Okay, so welcome to this new lecture, lecture number 9 in phase equilibria course. So we'll just recap what we did in the last class. So in the last lecture we were talking about binary solutions. Which are non-ideal. So non-ideal will mean that so you have three kinds of bonds. If you have AB binary solution, let's say AB, then you have three kind of bonds, AA, BB and AB, and depending upon whether or not the A and B have affinity for each other, that is determined by delta H mix. So depending upon whether this is positive or negative, so if it is negative, then you will have preference for AB bonds, and if you have positive, then AA and BB bonds are preferred. And this is manifested by another parameter, interaction parameter, which is omega. So if it is greater than 0, then you have positive delta H mix, and if this is less than 0, then delta H mix is negative. And depending upon these parameters, you have so if you draw the free energy versus composition. So if you plot, let us say this is XB, sorry. So if delta H mix is positive, then this is what is delta H mix going to look like. Okay. So this is delta H mix, and this is 0. So this is positive, this is negative. However, minus T delta S mix will look something like that. This is minus T delta S mix, and eventually the free energy of mixing may look something like what you have in between. So it might look, so this might be delta G mix. So depending upon the now you can have another situation in which delta H mix is negative. So if I draw another plot here, for instance, so you have another plot in which A and B are there, and if delta H mix is negative, so this is delta H mix, and if you have, this is delta minus T delta S mix, and eventually the free energy will be even further lower because both of the terms are negative. So this is delta G mix. So you can see the driving force, that is delta G mix, changes depending upon the relative magnitudes of delta H mix and minus T delta S mix with respect to each other. So if delta H mix is negative, which means the driving force for making a solid solution is higher, but if delta H mix is positive, the driving force for making the solid solution is lower. However, even at higher delta H mix, it turns out that in certain cases where you have situations like this, so positive, negative. So here delta H mix is greater than 0 and it's positive, and minus T delta S mix is also, it's negative, but it's not hugely negative because the temperature may be lower. As a result, the delta G mix plot will have behavior something like this. So it will not make a solid solution for throughout the composition range, but it will make a solid solution of A in B and B in A at certain. So what this tells you is that even though delta H mixing is higher and minus T delta S mix is not so negative, the delta G mix, when the solutions are dilute, that is, so this is A, this is B, so this is solution of, on this side you will have solution of B in A. So you have A as major element and B as minor element. On this side you will have solution of A in B. So B is minor and A is minor and B is major. So even though they preference for AB bonds is very low. Adding a little bit of B in A or adding a little bit A in B lowers the free energy, and this can be proved by, if you take the derivative for instance of del of delta S mix del XA, and if you try to make it XA tends to 0, this will be very close to infinity, and the derivative of delta H mix as a function of del XA when XA tends to 0 is equal to omega. So, since the change in entropy becomes infinity at pure compositions, so when you add very little, so this is XB tends to 0 and this is again XB tends to 0. So, very little amount of XB. So, at these compositions, since the free energy changes, entropy changes negative infinity, the free energy change tends to be, because the enthalpy changes finite and the entropy changes infinite, as a result the free energy tends to be negative at so basically these are the regions which are dominated by, you can say, regions dominated by minus T delta S mix contribution. So, configurational entropy changes a lot when you add little bit of impurity in something. So, you add little bit of B into A or little bit of A into B, the configurational entropy changes substantially. As a result, even at lower temperatures, impure material is preferred over pure state because of negative free energy of mixing in the impure state, dominated by the changes in the entropy. And so, as long as T is greater than 0 Kelvin, the delta G mix will always decrease for a pure component if you add little bit of impurity to it. So, that is why in nature pure things do not exist. Always everything will always consist of minute amounts of impurities which will lower the free energy of that particular phase, resulting in negative delta G of mixing, and which is mainly dominated by the entropy term, not the enthalpy term. And this is because of changes in configurational entropy. You can work this out using the delta S mix expression and delta H mix expression, which I have showed before. So, these two expressions, the balance between these two entities, delta S mix and delta H mix, will determine negative free energy of mixing at in the impure states. So, basically what you say that is, so now it's a recap is over. So, what we have here is basically that what we are concluding here is that dilute solutions or small additions of to pure element will result in a decrease in delta G governed by decrease in minus T delta S term, and mainly it is the configurational entropy that changes. So, as long as T is greater than 0 Kelvin, when you add impurity to a pure phase, pure metal or material, pure element, impurity addition leads to negative free energy of mixing, which means impure phase becomes more stable as compared to pure phase, and this is mainly dominated by increase in the configurational entropy. As a result, minus T delta S mix becomes more negative. However, this is only true about the dilute solutions, not about the highly impure solutions. So, in very small, the impurity has to be present in small quantities. Of course, the relative change will be governed by the value of delta H mix as well, but even though delta H mix is very positive, every system can tolerate small amount of impurities in it driven by thermodynamic changes. So now let us move to another concept. So what we have done is we have learnt about chemical, we have started from ideal solutions, and following that we have discussed the change in entropy, change in free energy of mixing in ideal solutions, and then we invoked the concept of chemical potential, which is basically the changes in the free energy when minute additions are made to an alloy of A or B, let us say. And then we looked at what happens when the solution is not ideal. It is a regular solution which has whose enthalpy of mixing is not 0. So delta H mix is not 0, rather it is positive or negative. So depending upon the magnitude of delta H mix and corresponding changes in minus T delta S mix, you will have a system's stability predicted. But in many cases, wherever delta H mix is negative, you will always have stable solid solution, and even though delta H mix is positive, depending upon the temperature and configuration entropy changes, you will have either complete range of solid solution which is thermodynamically stable, or at least at the ends of A and B you will have thermodynamic stability of impure phases. So this is what we have discussed so far. In this lecture now we take this forward by introducing another concept called as activity. So activity is basically very similar to chemical potential. It is a measure of how active an element is. So basically it determines whether or not that particular element would like to stay in the solution phase or it would like to come out of solution phase. So depending upon the magnitude of this activity, the solutions are made stable or unstable. So basically one can define activity in such a manner so that chemical potential is related to activity as GA plus RT ln AA, and mu B is equal to GB plus RT ln AB. This is for an ideal AB alloy, okay, alloy system, or basically or solution, solid solution. Alright. So mu A is equal to GA plus RT ln AA, mu B plus GB, mu B is equal to GB plus RT ln AB. So basically what we had earlier was that mu A was equal to GA plus RT ln XA and mu B was GB plus RT ln XB. We have replaced XA and XB by a term called as activity, which is AA and AB. Now in general, AA for regular solutions is less than XA and AB is less than XB, or you can have AA greater than XA and AB greater than XB. So depending upon how active the element is, your activity can be higher or lower than the atomic fraction of that particular element in the alloy. So in general they are not equal to XA and XB. A is not equal to XA, and graphically how do you represent it? It's like this. So you make a plot of free energy versus composition. So AB, in this direction you have XB varying. So when you plot, let us say, free energy of an alloy, right. So this is, let us say, point A, this is point B, and this line gives the rule of mixture free energy of alloy, okay. So basically this is, you can say, G mix GM, which was XA GA plus XB, Gb before mixing, all right. This point is Ga, this point is Gb, and in reality you form a mixture which is stable. As a result, this is what is delta G mix, and this is what we have done earlier. Activity is determined by, so you draw a common tangent, you draw a tangent, and this tangent intercepts on, so correspondingly you will have chemical potential for a given composition. Let us say this is x naught. So correspondingly you have chemical potential of A and chemical potential of B. So for this alloy of composition x naught, the chemical potential of A is mu A and chemical potential of B is mu B in the alloy for this particular composition, and correspondingly this term is minus RT ln AA, and this term is minus RT ln AB. So you can see that the previous relation, the Gb was equal to mu B minus RT ln AB, and Ga was equal to mu A minus RT ln AA, or so. So depending upon the activities, now we will see how these things add up. So this is how we define activity for a regular solution. We know that mu A is equal to Ga plus gamma into omega into 1 minus say square plus RT ln XA, and mu B is equal to Gb plus omega 1 minus XB square plus RT ln XB. So this term and this term, they are what becomes equal to RT ln. So RT ln AA is equal to omega 1 minus XA square plus RT ln XA, and RT ln AB is equal to omega 1 minus XB square plus RT ln XB. So if you now simplify this, what you get is ln AA by XA is equal to omega by RT into 1 minus XA square, and ln AB by XB by RT into 1 minus XB square, and this is assuming that A and B have similar structure. So now if you plot these activities as a function of composition, so this is as a function of composition. So let us say this is 1, this is 0, this is pure A, this is pure B. So this is XB and this is XA. Okay. So first thing I plot is AB, the activity of B in A. Okay. For an ideal solution, the activity of AB is equal to XB, and this is basically given by what we call as Raoult's law. Okay. And depending upon now delta H mix, whether it is positive or negative, the activity deviates. So if you have a non-ideal solution, then so this is for delta H mix greater than 0, which means the B is more active. A and B do not mix. So, when delta H mix is greater than 0, which means elements are more active. They don't like to stay in the bound form. They rather prefer independent forms. As a result, their activity is higher. Okay, and we will come back to this slope later on. So, basically this is delta H mix greater than 0, and second state that you might have is the other way around. When you have delta H mix less than 0. So, in such a situation, when A and B bonds are preferred, then A and B are not very active. As a result, the activity of B, for instance, is lower than its mole fraction, which is determined by the ideal solution Raoult's law. In this case, the activity is lower because of delta H mix being less than 0, and again we can draw a slope at this point. So, this is 100% B, this is dilute solution when B is very small. Okay. So, we can say that for ideal solution you can have, which is basically Raoult's law, AA is equal to XA and AB is equal to XB, and for non-ideal solutions to say if delta H mix is less than 0, then AB is less than XB. If delta H mix is greater than 0, then AB is greater than XB, and the ratio of so basically ratio of A versus X for a given element AI to Xi is called as activity coefficient of I. So, you can see that when element is in its ideal solution, so this activity will be gamma I. So, gamma I will be equal to 1 for ideal solution, and gamma I will be greater than or less than 1 depending upon. So, it will be later than when delta H mix is greater than 0, and it will be when delta H mix is less than 1 when delta H mix is less than 0, and this is what is called as Henry's law. So, Henry's law says that for a dilute solution of, let us say, A in B, okay, that is XA is tending to be 0, the activity coefficient of A in B, that is gamma A, is equal to AA by XA. Similarly, for a dilute solution of B in A, when XB is tending to 0, activity coefficient of B in A would be gamma B, that is equal to AB by XB. So, for dilute solution of B in A, gamma B will be equal to AB by XB. So, for this solution when XB is tending to be 0, so this is basically XB tends to be 0, and gamma A for such a system will be almost equal to 1. So, A, the majority element, will act as if it is like a ideal thing, and whereas the minority element, which is the dilute element, will act as per the Henry's law. So, this will act as per Raoult's law, and this will act as per Henry's law. You can also plot similarly the AA with respect to X. So, this is 1, this is 0, this is pure A. So, this is XB, this is XA. So, for a pure element, AA will be here. For pure B, AA will be equal to 0. So, ideal case would be, I am sorry, so this would be a straight line when it is ideal. So, this is AA is equal to XA. For now, you can have two more cases. The first case could be like this, the second case could be like this. So, in this case, this is AA greater than XA when delta H mix is greater than 0, and this is AA smaller than XA when delta H mix is less than 0. So, so this is at this point your XA is 1 and XB is 0, at this point XB is 1 and XA is 0. Okay. So, this is how it will vary. So, in this, so basically the activity of an element is equivalent to chemical potential so it tells you that basically both of them tell about the state of that component in the system. Both basically measure the tendency of the element to leave or remain in the system. Okay. So, if your A is greater than 0, it means mu is also greater than 0, which means tendency to leave the solution, and if A is less than 0, mu is less than 0, it is tendency to remain. And basically what it means is that when A is large and mu is large, the partial pressure of that element is high, and when A is small, mu is small, the partial pressure of that element is low. So, this tells you about the propensity of the element to remain or leave the system, both these activity and chemical potentials. We will stop here in this lecture. We will start the next lecture with the further moving on to the real solutions. So, we looked at ideal and regular solutions. Now, we will be looking at the real solutions. Thank you.